I'm going to tell you about a mistake so fundamental, so deeply ingrained in the way we think, that you probably made it this morning without realizing it. Maybe you're making it right now as you read this. And the scariest part? This single mistake, this basic flaw in reasoning, distorts absolutely everything you think you know about reality. The mistake is this: we confuse descriptions with the thing being described. Wait, let me explain why this is much deeper than it seems. When you look at the sky on a clear night and see the moon, you think, I'm seeing the moon. Simple, direct, obvious. But that's wrong. You are not seeing the moon. You are seeing light that was reflected by the moon about a second and a half ago, traveled 384,000 kilometers through empty space, entered the Earth's atmosphere, where it was slightly refracted and scattered, passed through the cornea of your eye, was focused by the lens, projected onto your retina, where individual photons struck photosensitive molecules that changed shape, triggering electrical signals that traveled through the optic nerve to your brain, where they were processed by billions of neurons running incredibly complex algorithms that your brain has spent millions of years evolving, and finally produced a conscious experience that you interpret as seeing the moon. You are not seeing the moon. You are seeing a representation, a reconstruction, a simulation of the moon created by your brain based on indirect data. Okay, but what's the difference? You might ask. In the end, I still know the moon is there, right? And that's precisely where the fundamental error lies. The difference matters, and it matters a lot, because you are constantly confusing the map with the territory. You are confusing the description your brain creates with the underlying reality. And this confusion literally contaminates everything you think about the universe. Let me give you an example that will make this crystal clear. Have you ever wondered what color an apple really is? Red, obviously. You can see it's red, it's right there. Red. But wait, what is red? Red is an experience that happens inside your brain. There is no out there in the world. What exists out there are electromagnetic waves with different wavelengths. The apple absorbs most wavelengths of visible light and preferentially reflects waves with wavelengths around 700 nanometers. These 700 nanometer photons are not red. They have no color at all. They are simply oscillations in electromagnetic fields. When they reach your retina, special cells called cones respond preferentially to these wavelengths. These cells send signals to the brain, and your brain, through processes we don't yet fully understand, creates the subjective experience you call seeing red. The color red isn't in the apple, it's in you. And here's what's really disturbing. Another person looking at the same apple might be having a completely different experience. What you experience as red might be completely different from what I experience as red. But since we can never directly compare our subjective experiences, we'll never know. In fact, some people are colorblind. They literally see different colors. Mantis shrimp have 16 types of color receptors, we have 3. They see colors we can't even imagine. Snakes can see in the infrared. Bees see ultraviolet. So what is the real color of the apple? The question doesn't even make sense. Color is a property of the interaction between light, objects, visual systems, and brains. It's not an intrinsic property of the apple. But we treat color as if it were real, as if it were out there in the world. And that is the fundamental error, confusing the description, the experience of red created by our brain, with reality, 700 nanometer electromagnetic waves being reflected. Now, you might be thinking, okay, color is subjective. I've heard that before. What's the big deal? The big problem is that this error isn't limited to colors. It's in absolutely everything. Let's talk about temperature. You pick up a glass of hot water, you feel that it's hot. The temperature is real, right? You can measure it with a thermometer. 60 degrees Celsius. Definitely. Real. It's there. But what exactly is temperature? At the fundamental level, temperature doesn't exist. What exists are trillions of water molecules moving at different speeds, colliding with each other, exchanging kinetic energy. Some molecules are moving fast, others slow. There is a statistical distribution of speeds. When you calculate the average kinetic energy of all these molecules, you get a number. And we call that number temperature. but it's a statistical description, an average, a mathematical abstraction that summarizes the collective behavior of trillions of particles. An individual molecule has no temperature. Temperature is an emergent property that only makes sense when you have many particles together. It's a useful human concept, a way of compressing information about a complex system into a single number. But it's not a fundamental thing that exists at the microscopic level. And here's where it gets fascinating. Different definitions of temperature can make sense in different contexts. In thermal equilibrium, we have classical thermodynamic temperature. In quantum systems, we have effective temperature. In black holes, we have Hawking temperature. In plasma physics, you can have different temperatures for electrons and ions in the same system. So what is the real temperature? It depends on the context, what you're measuring, and the theoretical framework you're using. Temperature is a description, not a thing, but we treat temperature as if it were a basic, fundamental property of reality. And when we do that, we lose sight of what is really happening. Let me give you another example that will really fry your brain. Solidity. You bang on the table. Solid. Definitely solid. It's there. It's matter. It's real. But we've talked about this before. Atoms are 99.9999% empty space. You never actually touch the table. It's electromagnetic repulsion. But there's something even deeper here. What makes the table seem solid to you? It's that the atoms in the table are arranged in a regular pattern, a crystalline or amorphous structure, and the forces between them are strong enough to resist ambient thermal energy. But solid versus liquid versus gas are not fundamental states of matter. They are macroscopic descriptions of how molecules behave collectively under certain temperature and pressure conditions. In fact, you can have intermediate states. Liquid crystals are simultaneously ordered, like solids in one direction, and fluid like liquids in another. Glass is technically a supercooled liquid that flows so slowly it appears solid. Plasma is a fourth state. Bose-Einstein condensates are a fifth, and there are others even more exotic. The division between solid, liquid, and gas that you learned in school is a useful simplification, not a fundamental truth about reality. It's a description that works well under normal conditions, but breaks down when you look closer or in extreme conditions. Do you see the pattern? Color, temperature, solidity. These are all descriptions, useful ways our brains or our science have developed to categorize and understand reality. But they are not reality itself. And here is the fundamental error, the error that distorts everything. We reify these descriptions. Reify means to treat an abstraction as if it were a concrete, real thing. We do this all the time without realizing it. Let's talk about things. You look around and see things, a chair, a table, a pen, distinct things, separate with clear boundaries. But where exactly does the chair end and the air begin? You might say, at the surface. But the surface is rough at a microscopic level. Atoms are constantly moving in and out. Air molecules collide and occasionally stick together temporarily. Photons are constantly being absorbed and emitted. Electromagnetic fields extend to infinity, though they weaken with distance. The boundary between chair and non-chair is blurred, arbitrary, and dependent on the scale from which you look. Even worse, the atoms that make up the chair now are not the same atoms that made it up a year ago. Background radiation is constantly colliding with and occasionally displacing atoms. Dust settles and is removed. Gradual chemical changes occur. So, is the chair really the same thing over time? Or is chair just a convenient label we apply to a pattern that slowly changes? In fact, this question becomes even stranger with biological objects. You replace virtually every cell in your body over the course of about 7 years. The atoms that make up you now are not the same atoms that made you up a decade ago. So, what makes you you? The pattern, the continuity of consciousness, the information stored in the arrangement of neurons. You are not a thing, you are a process. A dynamic pattern of matter and energy that remains roughly stable over time while its components are constantly being replaced. But we treat things as if they were fundamental, discrete entities with clear boundaries. And when we do that, we lose sight of the fluid, processual, contextual nature of reality. Now I'm going to show you how this error contaminates even our most fundamental concepts in physics. Let's talk about particles. Modern physics is often described as being about fundamental particles, electrons, quarks, photons, etc. Tiny balls of matter or energy, things. But that's completely wrong. Quantum mechanics does not describe particles. It describes quantum fields. The entire universe is made of fields. The electron field, the quark field, the electromagnetic field, etc., that permeate all of space. What we call a particle is a localized excitation in a field. It's like a wave in the ocean. The wave appears to be a thing. You can point at it, you can surf it, you can measure it. But the wave isn't really a thing separate from the ocean. It's a temporary pattern in the ocean. The water molecules that make up the wave now are not the same molecules that made it up a second ago. The wave is a pattern that moves through the medium, not a thing that travels. Similarly, an electron is not a small ball traveling through space. It is a localized excitation in the electron field, and this excitation has strange properties. It can be spread out in space, it can be in multiple places simultaneously, it can tunnel through barriers. But we use the word particle, and immediately our brain conjures up the image of a small, solid ball. And this incorrect mental image leads us to all sorts of confusion and apparent paradoxes. The famous double-slit experiment. If you fire electrons through two slits, they create an interference pattern like waves. But if you try to detect which slit the electron passed through, the interference pattern disappears and you see particle behavior. People go crazy trying to understand this if they think of electrons as tiny balls. How does the particle know if it's being observed? How does it pass through both slits? Does consciousness create reality? But if you think in terms of quantum fields, it makes much more sense. The electron's field propagates through both slits and interferes with itself. When you make a measurement, you force the field to localize to a specific point. You create an interaction that causes the field to collapse into a localized excitation. There is no magic. There is no consciousness creating reality. There are only quantum fields behaving according to well-defined mathematical equations. Our confusion comes from trying to force these quantum fields into the mental category of particles, tiny solid things that our ape brains evolved to understand. We are making a fundamental mistake, confusing our description, particle, with reality, quantum field. And this mistake is repeated everywhere. Space and time. We think of them as real, fundamental things, a stage where events happen. But general relativity tells us that space-time is a description of geometric relationships between events. And some interpretations of quantum physics suggest that space and time may emerge from something more fundamental. Perhaps quantum entanglement, perhaps information networks. Space and time can be descriptions, not things. Cause and effect. It seems obvious that A causes B. Billiard ball, A hits billiard ball B, causing B to move. Clear cause, clear effect. But at a fundamental level, there is no cause and effect. There are only correlations. The laws of physics are symmetrical in time. You can run them forward or backward. The distinction between cause and effect emerges only when you consider complex systems with many particles where entropy increases, the second law of thermodynamics. Cause is a useful description of statistical patterns, not a fundamental characteristic of the universe. Do you see how profound this is? Virtually all the concepts we use to understand the universe, things, boundaries, colors, temperature, solidity, particles, space, time, cause and effect, are descriptions, not fundamental realities. These are conceptual tools that we develop because they are useful in certain contexts. But they are not the underlying reality. They are maps, not the territory. And the fundamental error, the error that distorts everything, is forgetting this. It's treating our descriptions as if they were reality itself. This mistake has enormous consequences. First, it makes us think we understand things that we don't actually understand. You say, the apple is red, and think you've made a statement about reality. But all you've done is describe a particular subjective experience that your brain creates in response to certain wavelengths of light. Secondly, it blinds us to how strange the universe really is. When you realize that particles aren't really little balls but excitations in fields, that space and time may not be fundamental, that you are not a thing but a process, the universe becomes much more mysterious and fascinating. Third, and perhaps most importantly, it makes us less flexible in our thinking. We get stuck in mental categories, solid versus liquid, particle versus wave, cause versus effect, when reality is much more fluid, contextual, and strange. Quantum mechanics has forced physicists to confront this. Electrons are neither waves nor particles. They are something else that exhibits aspects of both depending on how you look at it. Light is neither wave nor particle. It's the same thing. And the most profound lesson of quantum mechanics is not about the strange behavior of particles. It's about the nature of knowledge and description. Niels Bohr, one of the founders of quantum mechanics, insisted that we cannot speak of quantum reality independently of how we measure it. We can only speak of the results of measurements. The underlying reality, if such a thing exists, is fundamentally inaccessible. This sounds like crazy philosophy, but it has real depth. Every description requires context, every measurement requires a choice of what to measure and how, and different choices reveal different aspects. It's like asking if a coin is showing heads or tails while it's spinning in the air. The question doesn't make sense. The coin is in a state that is neither heads nor tails. Only when you stop the coin, analogous to taking a measurement, do you get a definite result. Quantum mechanics generalizes this. Quantum particles don't have definite positions and velocities until you measure them. It's not that you don't know, it's that there are literally no definite values before measurement. Reality is fundamentally undefined until it is forced to define itself through interaction. This goes against everything our intuitions tell us. Because our intuitions evolved by dealing with macroscopic objects that seem to have defined properties regardless of whether we look at them. But our intuitions are wrong, or rather, they are useful descriptions that work in certain contexts but break down when we go beyond those contexts. So how do we get out of this fundamental error? How do we stop confusing descriptions with reality? The first thing is to cultivate what I would call epistemological humility. To recognize that everything you know about the universe is filtered through limited senses, processed by a fallible brain, expressed in mental categories that evolved for purposes completely different from understanding fundamental physics. You don't see reality directly. You see a model of reality constructed by your brain, and that model is useful, incredibly useful for navigating the world, but it's not reality itself. Second, always ask yourself, is this a thing or a description? When you say, this table is solid, stop and think. Is solidity an intrinsic property of the table? Or is it a description of how the table behaves under certain conditions in relation to you? Third, get comfortable with multiple descriptions. Light is a wave. Light is a particle. Both are useful descriptions in different contexts. Neither is the truth. You don't have to choose one. Temperature is average kinetic energy. Temperature is a thermodynamic parameter. Temperature is a measure of entropy. Different descriptions, all useful, all true in their respective contexts. Fourth, and this is subtle, recognize that the very distinction between description and reality may ultimately be a description as well. There may not be a fundamental reality separate from all possible descriptions of it. This sounds very philosophical, but it has concrete implications. Perhaps the universe isn't made of something fundamental that is there independently of observers. Perhaps it's a network of relationships, a set of correlations, a mathematical structure. Some physicists take this very seriously. The hypothesis that the universe is mathematical, not that the universe is described by mathematics, but that it literally is a mathematical structure, is gaining traction in some circles. If this is correct, then the distinction between map and territory collapses. The map is the territory. Descriptions are all that exist. But even if you don't go that far, the point remains. Be very careful about what you reify. Be very careful about treating descriptions as if they were real things. And here's the beautiful irony. Modern physics, the most successful description of reality we've ever created, works precisely because it doesn't make that mistake. Physicists don't ask, what is an electron really, in a profound philosophical sense. They ask, how do electrons behave? What equations describe this behavior? And what predictions can we make? Physics is explicitly about building mathematical descriptions that make accurate predictions. And it works incredibly well. But when people try to interpret physics, to extract what is really happening, they often fall into a fundamental error. They try to reify mathematical descriptions. They try to transform abstract symbols into small, solid balls moving through space. And then they get confused. How can it be both wave and particle? How can you be in two places at the same time? How does the observer affect reality? The confusion arises from trying to force mathematical descriptions into inadequate mental categories. Reality, whatever that ultimately means, is what it is. Our descriptions are tools for navigating it, predicting it, manipulating it. Different tools for different jobs. No single tool captures everything. And perhaps, just perhaps, there isn't everything to capture. Perhaps it's descriptions all the way through. So here's the final lesson, the most important thing. The fundamental error that distorts our view of the universe is forgetting that we are always describing, never directly accessing, reality itself. Color, temperature, solidity, particles, space, time, cause, yourself, all useful descriptions that work in appropriate contexts, but break down when pushed too far. Reality doesn't care about our categories. It doesn't care about our intuitions. It doesn't care whether it makes sense for evolved creatures to hunt on the savannah. But we can build increasingly better descriptions. We can expand our conceptual frameworks. We can recognize the limitations of each description and develop new ones when the old ones become inadequate. This is the story of physics. Not discovering the ultimate truth, but building increasingly better, more comprehensive, and more precise descriptions. And the key to this progress is to always remember, it's just a map. It's not the territory. The territory, if such a thing truly exists, remains fundamentally mysterious, always beyond complete comprehension. And perhaps that's exactly how it should be.